Alright, welcome back everyone. In this video, I want to give a proof that the square root of 2 is irrational. And really what I mean by that is that there's no rational number, in other words, no fraction of integers, such that if I square that fraction, I get exactly 2. Right? And I want to do a completely rigorous proof of this. You've probably seen proofs before that kind of appeal to even and odd, and we're gonna use those ideas too, but I want to break it up into 2 steps. So I want to use what's called a lemma in math. So a lemma is a statement that's kind of a piece of a bigger whole. So a lemma is usually a small statement. It usually has a short proof, and it's often nice to kind of prove these separately so that we don't clutter up the main proof with these statements, right? And so we have lemma 1 says that every integer is either even or odd. Okay. And we haven't really defined even or odd in this class. And so rather than write even or odd and kind of specify those definitions, let me do that all at once in this statement. Right? So it's either of the form 2k for some integer k, or else of the form 2k plus 1 for some integer k. And what we're going to do is we're going to call, and maybe I'll just denote this in green, any number of this form is going to be called even, and any number of this form is going to be called odd. Okay. And just, I'll erase this in a second, but just to kind of show you what we're talking about, if I take a number like 8, that's 2 times 4, so that would be even. If I take a number like -7, that's equal to 2 times -4 plus 1. So this is of the form 2k plus 1, and therefore it is going to be odd. Okay. Right. So this is something you may have taken for granted, that every whole number is either even or odd. Well, we're going to have to prove it. Right? So we're going to write a proof of this fact, and so let's do that. So let's write a proof. Okay. Proof. And so step 1, let's just note that 0 is even, since 0 is equal to 2 times 0. Okay. So we have to show a statement for every integer, and let's just get 0 out of the way, right? So 0 satisfies this condition, so we're done with 0. Step 2 is going to be use induction to show that every natural number is either even or odd. Okay. And then step 3, which I will not do in this video. I encourage you to do this on your own, is use induction or another argument to show that every negative integer is either even or odd. Okay. And maybe I'll just say just a second here. You know, if you, for instance, if you know that 7 is odd, right? If you know that 7 is odd, then maybe you can think about how you could show that negative 7 is also odd, right? And so maybe you have to think about, like, well, 7 is going to be 2 times 3 plus 1, and negative 7, well, I guess it's going to be negative 2 times 3 plus 1. And then you can maybe think about how that's 2 times negative 3 minus 1. And then if we really want to get it in the form of 2k plus 1, we just have to change this negative 3 to a negative 4. Okay? So if you didn't want to do a full-blown induction proof, there is a way to kind of show how writing a positive integer in this 2k or 2k plus 1 mode transfers over to the negative case as well. Right? So I'm gonna leave that one to you, and I'm just gonna prove step 2. Okay. So step 2 says use induction to show that every natural number is even or odd. Okay, so let's proof by induction. All right, so step 1 is we do the base case. That's going to be P1. And we better write out our statement Pn. Right? So what is statement Pn? Pn is going to be the statement that n is either 2k or 2k plus 1 for some integer k. Okay. So we want to show that for every natural number that this is true. And so the way we prove that by induction is we start with P1. So P1, let's see. Okay, so 1 is equal to 2 times 0. 0 is an integer plus 1. Good. So we've shown that P1, which is this sentence, that 1 is either 2 times something or 2 times something plus 1. We just checked that. So we finished the base case. And now let's do the inductive step. So the inductive step is going to be, suppose Pn, so i.e. let's suppose that the number n is either 2k or 2k minus 1 for some k. Okay. Maybe I'll do k as an integer. I'll use this symbol. Okay. And then what do I want to show? Well, I want to show statement Pn plus 1, right, which is going to say that n plus 1 is either 2 times an integer or 2 times an integer plus 1 for some integer in z. And notice that I used a different letter here, right? Because it's going to be a different number, right? If I take a number and I add 1, just think about it. If I take 9, which is 2 times 4 plus 1, and then I do n plus 1, right? If n is 9, and I go to n plus 1, that's going to be 10. And 10 is going to be 2 times 5, right? So the letter that I'm using, in this case this is 2k plus 1, well, down here when I get my multiple, well, this is some different number. And so that I may need to understand that for my proof, but just so I don't get confused, I'm gonna write it with a different letter in my statement. Okay? So, okay, we want to show, okay, so what are we supposing? I'm supposing n is either even or it's odd. Okay, sorry about that, so sorry, I meant a plus. And then I want to show that the next number is either even or odd. Well, let's see. Okay, so I know, so there are two options. So case 1, n equals 2k, and case 2, remember there was an option for n. N was either even or it was odd. Okay. Well, let's try case 1. If n were even, if n were equal to 2k, well then n plus 1 equals 2k plus 1. Oh, we're done. Right. We're done since we wrote n plus 1 as 2 times an integer plus 1. Right? And maybe you don't even need to write this statement down here, this explanation. I'm just really going into a lot of detail in these proofs to show how we're verifying things, right? So we just showed if we start with an even number and we add 1, we get an odd number. Okay? Now case 2, what if we start with an odd number and then we add 1? Okay, well if we start with an odd number, then n plus 1 is going to be 2k plus 2, and that's 2 times k plus 1. And again, we're done. And why are we done? Since we wrote n plus 1 as 2 times an integer. So remember, our goal is just to show, let's go back to our goal. Our goal was to show that n plus 1 is either twice an integer or twice an integer plus 1. Right? And we did that in both cases. Right? And so now let's do our conclusion. So therefore, we have shown that if Pn is true, then, remember our if-then statement, Pn plus 1 is true. So by induction, we are finished. Awesome, awesome, awesome. So that's our proof. And let's go back and remember what we proved. We proved that every number is either even or odd. So you may have taken that for granted, and that's fine, that's fine. We're not going to prove every single tiny statement like this, but we could. And that's what's so cool about math, is that if someone asks you, could you really prove that every integer is either even or odd? Yeah, you could. And that's what we just did. Right? So that was lemma 1. I want another lemma here, and I think I might leave that one to you. I think I might put that on the homework for you. And so lemma 2 says that if a is an even number, then a squared is even. And if a is odd, then a squared is odd. Okay? And this, again, seems completely reasonable. If we square an even number, the square should still be divisible by 2. And if we square an odd number, well, I guess that's of the form 2k plus 1. When we square it, we could do some algebra, and we might see that that's still of the form like 2k, or 2 times, it'll be a different k, but 2 times an integer plus 1, right? And so I'm gonna put this on the homework. And now with these two ingredients, we're ready to prove our final theorem of the video, which is that there is no solution x in the rational numbers such that x squared equals 2. Right? So we're going to see how both of these ingredients come into play. Okay. So let's write our proof. Right? So we're going to argue by contradiction. So I can make this bigger. Argue by contradiction. Right? And so contradiction means we're gonna assume the opposite, right? So this statement says there is no solution. So what's the opposite? What's the opposite of there is no candy? Well, there must be some candy. Right, so the opposite of there is no solution is we're going to suppose there is a solution x equals a over b, right? And we want this to be a rational number, so we had better take the numerator and denominator to be integers with x squared equals 2. Right? So we're going to assume that we have a solution to this problem with a rational number. And at some point in our proof, I'll kind of put it down here, this is a contradiction. We're going to be looking for a contradiction. And so I'll put this kind of lightning bolt thing down here. We don't know where it's going to happen. We hope it happens. But we're going to see that somewhere in the proof, there's going to be a contradiction. Because obviously, like, if we're trying to show there is no solution, and we assume that there is, then that can't possibly be consistent. Right? Good. And so we're going to suppose there is a solution, and we're going to add actually one more hypothesis, right? And with a over b in lowest terms. Okay. Now, what I mean by lowest terms, I'll just say that in words, since I think we know what that means. It means that a and b have no common factor. So we assume that the numerator and denominator don't have a factor of 2 or a factor of 3 or a factor of 5 or anything like that. Right? And from this, I promise you, we will get our contradiction. Right? Okay, so what do we know? Okay, so we know, so we are given that x squared equals 2. That's equivalent to, that's what this little arrow means, equivalent to, or if and only if, it's equivalent to saying a over b squared equals 2. Okay. And now if a over b all squared is 2, okay, well that's going to be the same. It's going to imply that a squared equals 2b squared. Okay. And let me just get this contradiction out of the way for the moment. And now once we have this, we know that a squared is even. Right? Look at it. It's a squared is 2 times an integer. So that must mean that this right-hand side is even. So the left-hand side, which is a squared, must be even. So we have an even number, a squared. And now let's go back to our lemma. Lemma 2. If a, if a is either even or odd, and if it's even, a squared would be even. And if it's odd, then a squared would be odd. And so the only possible way we could get an even a squared would be if a is even. Right? Right? Okay. So let's write that carefully. So by lemma 1, a is either even or odd. Remember, that's a lemma that we took some pain to prove, that every number was even or odd. And by lemma 2, since a squared is even, a must be even. Okay? Very good, very good. And so that must mean, so a is equal to 2k for some integer k. Okay. All right. So now let's take this highlighted thing and plug it back in to our equation up here. All right. So therefore, 2k squared, that's a squared, has to be 2b squared. Simplify it. 4k squared equals 2b squared. I'm not ready for our contradiction yet. I promise it will come. And there, now we can divide by 2. 2k squared equals b squared. And now we're in the same thing, right? So this is now implies that b squared is even. And as before, lemma 1 and lemma 2 imply that b must be even. B must be even. And so now what do we know? So let's pause and notice. So note that A and B are both even. Okay, we said A must be even. We said B must be even. But we also assumed that A over B was in lowest terms. This is a contradiction, right? If we have two even numbers, then they have a common factor of 2, and then the fraction can't be in lowest terms. So we've reached our contradiction. Now if we go back to our proof, what did we assume? Okay, so we're going to argue by contradiction. Okay, so suppose there is a solution. We suppose there was a solution. Okay, maybe that's what was wrong. Yeah, we suppose there was a solution. Yeah, that's the only thing we assumed. Right, the only thing we assumed was that we had a solution in lowest terms. If there were a solution, we could definitely put it in lowest terms. There's no problem there. So the only problem must have been in that supposition that there is a solution to that equation. And so let's conclude our proof. Therefore, there cannot be a rational solution to x squared equals 2. Okay. So I know this video did like a deep dive really down the rabbit hole in all of these little details, but I think it's good for us to start writing proofs at this level of detail to really get practice with our writing and things like that. So thank you for watching. Comment, subscribe. Let me know if you have any questions, and I will see you soon.